Good afternoon, everyone. Thank you for being here. I'm In-Cheol Han, the leader of Quantum Project team. I will be facilitating today's forum.
네, 안녕하십니까. 방금 소개받은 정재호입니다. Welcome to the 9th Yonsei University Quantum Computing and the Biohealth Forum today. And we are grateful for today because we have world-renowned chemistry and esteemed scholar in the field of chemistry. So with that, I'd like to invite Professor Kenneth Mertz to the podium, and please give him a big applause. Thank you.
Thank you. Thank you for those nice comments. I have to say I'm feeling really embarrassed right about now. I adapted this talk from a talk I gave in Japan, so I apologize. I do know that Seoul is in Korea, so sorry for that mistake. I truly am a little bit embarrassed. So it's really wonderful to be here. I've been to Korea many times. I counted maybe 8 or 9 times, but it was all at the airport. So on the way to different locations. So this is actually the first time I've stayed in Korea proper, down at Seoul, and I'm here with my daughter. She's 24 years old and is very much into Asian fashion and style and food, and so we've been enjoying our visiting Seoul for quite a bit. I also want to congratulate Yonsei on the installation of your new quantum hardware. I mean, that's really a very significant event, and you're one of the few locations in the world that has a quantum hardware on site. It may not be the one we choose in the end, but it's a really major milestone. So my deepest congratulations to you on this achievement. So today what I want to do is I'll tell you a little bit about Cleveland Clinic, because I get this question all the time: why did a hospital get involved in quantum computing? So I'll give you a little bit of the history of Cleveland Clinic, which goes back to, as you mentioned, to the Severance Foundation, which was also in Cleveland. And then I'll tell you a little bit about kind of my perspective on quantum computing, and then I'll highlight some research we've done that the first paper just came out on arXiv, and I'll show you where that is. And we have another paper that we're finishing now in collaboration with IBM that should be on the arXiv in the coming weeks. So with that introduction, let's see if here we go. So we have this saying, and I don't know, there's maybe a Korean variant of this, a long and winding road. So how does a hospital, why didn't MIT or Caltech do this? So how did a hospital actually end up getting into quantum computing? And it's actually quite an interesting story. So a little bit about Cleveland Clinic. It's a worldwide hospital system, initially founded in Cleveland right after World War II, right? World War II saw just amazing slaughter, and the physicians had come back from World War I and wanted to set up a more integrated hospital, and that was established in Cleveland. We have branches in Toronto, branch opened in London just recently, Abu Dhabi, and also in Florida. And you can read some of the statistics. It's one of the largest hospitals in the United States. Usually when they rank hospitals, Mayo Clinic, many of you have maybe heard that, in Minnesota, is usually ranked number 1, and Cleveland Clinic is number 2. And I'll tell you a little bit about their accomplishments in Cleveland. So Cleveland had several major accomplishments: the discovery of serotonin, which is important in sort of mood disorders and things like that. Kidney dialysis was pioneered at Cleveland Clinic, so this is used all the time now, saving many, many patients worldwide. Angiotensin II and hypertension. So Cleveland Clinic's really famous for heart disease. When I was interviewing and visiting, I was in there in the breakfast area, and I just bumped into a person there, and he was actually there for open heart surgery he's going to have in a few days, and he was eating breakfast, and it turned out he was from Egypt. He was a businessman there, and he came to Cleveland Clinic to have the surgery done, the open heart surgery done in Cleveland. So again, very famous in heart surgery area. So how did they get in quantum computing? Well, Ohio is part of the American Midwest, and the American Midwest had many factories related to the auto industry and steel and things like that. But with global competition from Japan, Korea, and many other countries in the world, that kind of industry has gone down. So there's a great interest in expanding into more high-tech areas. So there was a partnership formed between Cleveland Clinic and the state of Ohio. It's called Jobs Ohio. It's about a $500 million influx of money over 10 years. And they really wanted to create in Cleveland an innovation district. And Cleveland Clinic is the anchor of this. So you have kind of a road going in where there are various kinds of startups and companies are starting to set up shop in the area. So this really started a search for, well, we have this Jobs Ohio, who can we collaborate with? And so the logical partner, and Cleveland Clinic looked at many partners in the end, but the logical one, it was IBM. They had many interactions with IBM, with the Watson system, and they decided to continue that. So part of this Jobs Ohio, led to collaboration with IBM. And IBM needs no introduction here. Everyone, I think, is very familiar. You've just recently purchased or leased one of their hardware platforms. But this is a very well-regarded company with multiple Nobel Prizes, Turing Awards. Metal Technology is the highest award for technology in the United States. Again, the National Medal of Science recognizes great accomplishments in science. And they've actually led in patent leadership for a huge number of years, which I find to be incredibly remarkable. So they decided to collaborate with IBM. And this is, again, was a 10-year collaboration. There's, I think, $150 million is put into this collaboration between Cleveland Clinic and IBM, both in presence of hardware, so placing a Cleveland Clinic, a quantum computer, but also personnel. So I had the luxury and I'm blessed with the opportunity to collaborate with leading scientists in IBM. We actually have liaisons between Cleveland Clinic and IBM to help support the research program that I'm going to tell you about. So the aspects of the collaboration, there's research collaboration and commitments. There's a strong focus on AI, machine learning, digital technologies, hybrid cloud. The other thing that I think is really important, I think in our conversations right after lunch, is training and outreach, right? The new workforce, there's just not that many people that are trained in quantum computing and quantum information science. And this is going to be a field for the young people in the audience. This is going to be a field that's going to play a big role in your scientific life going forward, right? As this technology matures. So it's really essential to train people to use this really novel technology. In some ways, you should think about it like this is like the 1970s with integrated circuits, right? You have this new technology, and it's going to be the task of the younger generation to really figure out where this can be applied and how it can make a difference in today's world. We have a quantum program, so we gained immediate access to IBM's quantum systems. So I have access to the IBM hardware that's in the cloud. And we also had a system installed, which I'll show you a picture of in a second. And we're going to have, in the next few years, the System 2 installed at Cleveland Clinic. Overall, we're truly blessed with incredible support from IBM, both in the education, but also in the hardware. The ability of my group to come up with some thoughts and ideas and immediately try it on quantum hardware has just really been truly remarkable. And I think that's something here at Yonsei that you're going to be blessed with, right? You're going to be able to come up with some ideas, try it on the hardware, and see how this works for you. So the areas we're collaborating with in terms of collaboration, high-performance computing. So today I'll tell you about quantum-centric high-performance computing and what we could do with that. There's AI, artificial intelligence, and quantum computing. My group is heavily working in this quantum-centric quantum computing. So these two areas. And I also have several people in my group that are doing quantum machine learning. And I won't have a chance to tell you much about that today. But that's kind of the research areas that we're involved in. So this is the first device that was installed. It's an Eagle processor. It's identical to the machine you have here at Yonsei. Did you get the light pattern, or do you have the dark machine? You have the Darth Vader machine. Okay. So, but yeah, so Cleveland Clinic wanted a light color pattern because we're all about curing patients and seeing the light. So this is the first kind of hardware installed outside of IBM in the United States. A couple of interesting things about this: the glass is from Venice, so Venice is famous for Murano glass. The typical machine has the top is open, but they had to put glass on the top as well because this was installed in a cafeteria. So you literally can walk over and, if you want, throw a paper airplane on top of it, right? It's in a former cafeteria. So it's every now and then when I want to get inspired, I walk down and take a look at the device. So IBM, I think, and people here are extremely familiar with it, and we had a nice discussion about different hardware vendors. IBM is probably unique in the sense, and I think some other vendors are doing this now, they actually give a roadmap. And so we're here at 2024-25. This is the Eagle processor and Heron. We've had some ability to run on a Heron processor, very nice device. None of these actually have error correction explicitly on the hardware. They're all error mitigation. And I'll tell you about a unique way in which we do error mitigation with our calculations. But the important thing for me, if you look at 28, 29, 30 in the next 4 or 5 years, we're going to have hardware error-corrected devices. So right now, we have to really fight errors with our algorithms, but IBM is anticipating delivering this in this time frame. I think their plan here is very aggressive. They've hit all their roadmaps, all their targets to date. So I'm very optimistic that in not too many years, we're going to actually have this error correction capability right on hardware and hundreds of qubits. And again, because qubits, the power of these devices scale with the number of qubits, the more you have, the more power you have. But that said, we currently have an Eagle device down here, and in the future we'll get probably a Heron or a Flamingo. That's to be determined. So the other companies are involved in this. I just list a few. There's many others. We talked about several other companies. We'll see. It's going to be really exciting in the next few years. Many of them had roadmaps or suggested they wouldn't have really good hardware until, say, 2030, but now many of them are saying they're going to deliver error correction in around 2030 as well. So it's going to be a really hectic, say, 5 years in the hardware side of things as well. So my group currently is working in these 3 different areas, so quantum simulations, quantum machine learning, and optimization. We sort of abandoned a little bit of the optimization because we found a lot of the sort of VQE-based methods, as I'll highlight, really cause a lot of errors to accrue and aren't very stable for the kinds of problems we want to do. So this area is a little bit kind of put to the background for right now. So again, today I'm going to talk mostly about, or exclusively about, quantum chemistry and not material science applications, but healthcare and life sciences applications. And before I jump into that, I should talk a little bit about the group. So the people that are doing this, so Daniel Kaliakin right here, Akhil Shajan, he's been driving a lot of the effort, Susant Das and Zen, and the quantum machine learning people are Hong Ni and Gurinder. I don't have a picture of him. My funding is from the NIH and the NSF. The nickname for my group, this was actually given to us by IBM folks. We're called Team Sonic because we like to move really fast. And also Sonic, if you see, he looks like he's entangled, right? So he looks like he's behaving in a quantum way. So I wear this title very proudly in terms of my group. So, it's really worthwhile, I think, spending a little time thinking about kind of where we've been and where we're going, right? So back when I was early 20s, I joined a group here that it was one of the 2 groups in the world that had a VAX 11780 in its lab. John Popel, who eventually won the Nobel Prize, had an 11780, and Michael Dewar's group at the University of Texas. And this is, again, the Moore's Law, and you can see that basically down here, in 1980 or so. This wasn't a particularly fast machine, but it was, for the time, it was incredibly fast, and it was ours. We could do whatever we want with it. Even that, we couldn't really do very sophisticated calculations. Benzene was a really difficult problem to calculate. But it was I think this is really a beloved machine in the community in terms of compute power. When I was towards the end of my PhD, we got a call from a company called Cray Research. And they were like, hey, we have this new machine. It's a vector machine. Can you get your code working on this device? And at the time, my friends in grad school all thought I was crazy for getting into theoretical chemistry because there weren't many jobs at the time, right? And so I was sort of not going to have a very bright future. But Cray came along, and this is 500 times faster than the VAX 11780, right? So benzene that maybe took a couple days to do now took a few minutes. So it was a huge, huge sea change. And then later on, parallel computing, Cray TE3E. I'll tell you a little bit more about that in the next slide. And nowadays, in the 2020s or so, we have NVIDIA GPUs, which really aren't on this graph, but this is sort of just the timing of these. And we're doing a lot on GPUs. And then I have here at the end, in 2024, we're gaining access to IBM System 1, 127 qubits. This is not to imply it fits on the Moore's Law. It doesn't. But this is kind of the current generations of machines. So a little bit about these. So VAX 11780, it's this top machine on the left. This, kind of ugly looking thing, I guess. It was 0.2 megaflops, right, was the power rating. We got a hold of the Cray. The Cray was about 100, 150 megaflops, so about 500 times faster. And as an assistant professor, I got a hold of a Cray T3E with about 1,000 CPUs. Each CPU is as fast as a single Cray XMP. And I had 1,000 of them, right? So 1,000 times faster in principle. And down here, recently we've been doing some quantum chemistry on Hopper GPUs. This is a 60 teraflop machine. It's about 400,000 times faster than the 11780, right? So this is the kind of increase in power that we've had. But now this graph here shows the performance in VAX 11780 units. So basically, the current CPU chips are about 40,000 times faster than, so this would be like a Pentium class chip. But if you notice, it's really plateauing. And so silicon is quickly plateauing, and we need something new to really keep pushing the boundary for compute power. So is quantum computing going to be that step forward? So let's see if I can get this movie to work. So I'm interested in healthcare, life science, computer-aided drug discovery. And so one of our goals is we want to be able to compute protein ligand interactions using quantum hardware. And the first thing you do is you look at, this is Crixivan bound to the HIV protease, and you can see you have things like hydrogen bonds. I can't really get, so you have van der Waals interactions here, some more van der Waals interactions. And then down here, you'll see some hydrogen bonding interactions. So typically when drugs bind to a protein, you're going to form dispersion interactions and hydrogen bond interactions. So we really wanted to first just ask the question, can we use a quantum computer to compute dispersion interactions and hydrogen bonding interactions? At the point where we looked at this, no one had really done this. So it wasn't known if it could be done. People had tried different things, but weren't particularly successful. So we decided that we would tackle a very simple system. We're going to tackle the methane dimer, which is the model system for dispersion, van der Waals interactions, and the hydrogen bond interactions defined by the water dimer. Again, very, very simple, but if you can't do these, you're not going to do a protein ligand system, okay? So how did this work out? So a couple things we should think about first. So in quantum chemistry, so this is a quantum chemistry application, there's two types of correlation that you need to consider. So if you think of like the nitrogenase cluster or if you think about photonics, things that are very, very important in the Korean industry. This is a static correlation problem in the sense that you need to consider all the possible electron configurations for the system you're interested in. So if you're looking at exciting an electron in a double bond to the pi star, you need to mix those two states, right? So this is static correlation. Static correlation is really important in materials, photonics, many, many areas, but it's not particularly important in drug discovery. Drug discovery is not driven so much by static correlation unless you have, say, a transition metal that you're going to bind your drug to. What is more important in drug discovery are dispersion interactions and hydrogen bonding, and this is really defined by dynamic correlation. So basically, it turns out typical quantum chemistry calculations, they have a flaw, like DFT, things like that. They don't incorporate dispersion interactions correctly. Dispersion interaction is just sort of mutual repulsion of electrons. So as you bring the two methane molecules together, the electron clouds deform and move their electrons around to respond to the fact that you're bringing this other molecule that has electrons close to it. So, again, in the quantum computing area, most people want to talk about static correlation. If the only thing you can do is static correlation on quantum hardware, that's never going to get you into healthcare and life sciences. It's going to be great for material science, but we really need to be able to handle this other type of correlation. So basically, initially, we started out using something called the variational quantum eigensolver, which is more of an optimization algorithm on quantum hardware. We found, like, for this particular system, it didn't work very well. And Jay Gambetta, who's the head of IBM Computing, I met him at Cleveland at a meeting, and he said, you need to talk to this group at IBM, led by Antonio Mezzacapo. So Antonio's here. Javier is here, and Mario Moto. So Javier is the first author in this paper, Mario is the second, and Antonio is the corresponding author. This is a collaborative project done with the group at RIKEN, which I had just come from. I just spent 4 or 5 days visiting RIKEN, talking to their scientists. So this paper, I think, to me, is a landmark paper. It's called Sample-Based Quantum Subspace Diagonalization. It's quantum-centric quantum computing. And instead of doing optimization, what they're doing is they're using the quantum device to pull out samples of the Slater determinants in a particular type of calculation. And I'll get into that in a little bit more. Ella she's sort of the fearless leader. She basically coordinates between IBM and Cleveland Clinic. Excuse me. And she's the one that gave this team the Team Sonic logo. So basically, we met with this team on a Friday afternoon at 4 o'clock. And for the first 6 months I was at Cleveland, we were just VQE, 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 right? And by 5 o'clock, when we finished the talk, we then had a post meeting, and we decided we're going to abandon VQE completely, and we're going to use this squeeze approach. And hopefully I'll convince you that that was a smart move. So over the weekend, we sort of got the software together. We had several meetings to think about the theoretical aspects of it. But this paper, it came out in arXiv. The archive's here. And the important thing is they are able to do things like the nitrogen bond breaking. And again, this is a static correlation problem. They're able to model iron-sulfur protein clusters, both 2 iron, 2 sulfur, and 4 iron, 4 sulfur. Importantly, instead of being stuck with 4, 6, 8 qubits, they were able to go up to 77 qubits. And in particular for this 4 iron, 4 sulfur, they're able to show quantum utility. So basically, the quantum approach was better than the classical approach, which is really important. So building off of this, we wanted to go after dynamic correlation. So this just summarizes things. So VQE basically is confined to very simple molecules. It only can handle 2 qubits, 4 qubits. I think some people have gone a little bit higher in qubit count. But again, you're really, really limited. And you're never going to get that quantum exponential power using small number of qubits. And even when you get it to work, the errors can be quite large. So if you compare a VQE calculation versus a classical version of that, the errors can be 4 kcals per mole, even on 2-qubit experiments. Squeezed, on the other hand, so I'm sorry, some of these will be SQSD and others SQD. Basically, it's the same algorithm. We now call it SQD. So basically, I think this is, and I'll hopefully convince you, there's a broad range of applications using this method, even potentially drug discovery. We can routinely use circuits of 20 qubits and more. We've done some experiments on cyclohexane, which I won't talk about, up to 77 qubits. Importantly, the variation between the classical version of that calculation and the quantum computing version using SQD algorithm, the errors are less than 10 to the minus 4 kcals per mole. That's kcals, not Hartrees, kcal per mole. So essentially they're identical, and I'll show you a number of examples of where this is true. Okay, so I'm not going to go into like circuit design in detail. If people want to talk about like the ansatz, we can discuss that. If you're really, really interested in some of the super quantum information technical details, I can connect anybody with Mario Moda, and he is sort of kind of our QIS expert on this project, and he'd be more than happy to speak with you. But I'll give you sort of just a general sense of what we're doing in this quantum-centric approach. So we basically take an optimized geometry for the methane dimer, and then we use 2 programs. We use PySCF to do the Hartree-Fock calculation. PySCF, I think it's Garnet Chan's program, if I'm not mistaken. You can download it for free, et cetera, and it'll create a file that has 1 electron, 2 electron integrals in the microorbital basis set. It's called an FCI dump. In this, we're going to be doing CI, or configuration interaction calculations. We also use something called AVAS. These are going to be configuration interaction calculations within an active space. So an active space, if you think about ethylene, the pi bond and the pi star bond, that could be the active space you're studying. So in these more complicated systems, the active spaces get trickier to deal with. So having an automatic program to help you define your active space is really essential. So AVAS is a program to use. There's multiple versions of this kind of program out there to do this kind of thing, but we happen to use AVAS. So then we get this FCI dump, and then we use a program called DICE, D-I-C-E. This has stochastic heat-bath CI or heat-bath CI capabilities. We're going to take our active space, we're going to do the CI calculation using DICE, using this stochastic heat-bath CI, and we're going to get a ground state energy. So this is the comparator that we're going to compare our quantum calculations results to. So this is all done on classical hardware using this DICE program. So in the quantum-centric approach, we do things a little bit differently. We take this and we place it onto the quantum hardware using a localized unitary couple cluster JASTRO ansatz. This is an algorithm developed by Mario Moda, so if you're interested in some of the technical details in the gate structure and things like that, he can help and discuss that with you. So what does this do? It's a couple cluster approach. You put this ansatz on the quantum hardware, and then you don't do any optimization. You don't ask it to optimize your wave function. You simply ask it to give you Slater determinants. So what is a Slater determinant? A Slater determinant is a mathematical object that tells you where the electrons are in the molecule in a qualitative sense, right? And basically, if you think about these Slater determinants and sort of doing these calculations, if you think of a molecule like propane using a STO3G basis set, very small basis set, there's about 1 trillion Slater determinants that you could determine from just propane using a small basis set. But what we do with this is we pull out about 100,000, depends on the application. Most of these will be about 100,000 Slater determinants. We pull these Slater determinants off the quantum hardware, and these Slater determinants are informed by this LUCJ ansatz. The other thing, too, is these calculations don't use STO3G. These are done using AUG-CCPV-QZ, a very large, chemically accurate basis set. So the calculations that we're doing on the quantum hardware today, that I'm describing, are using realistic basis sets, not toy basis sets. So we generate these bit strings. Now these bit strings describe Slater determinants. The important thing about these is you can apply a mathematical operation to these Slater determinants and determine how many electrons that Slater determinant is describing. If it's wrong, then instead of saying if your molecule has 10 electrons, it says it has 11 or 12 or 9 or 8, you know that an error occurred in your quantum hardware. So what you can then do is you can engage in a post-processing error mitigation strategy by taking these bit strings, and you can flip the bits. You can go in and say, based on, say, orbital occupancy, say, this bit I'm going to flip. And by flipping it, you go from 11 electrons to 10 electrons. So you've error corrected your quantum hardware. Error appeared, you have a clear way to do it. And this is all done on classical hardware. So then what we do is, through this error mitigation, we take our 100,000 bit strings, we usually bin it into 10K sub collections, right? So we'll have 10 samples of 10,000 bit strings. We then actually do, again, using PyCF or DICE, we do CI calculations. These are called select CI calculations in particular. And then we go through for each one of these 10, we get a result. We then take that information to help us inform the error recovery, again, by getting updated orbital occupancies. And we loop through this. I think Mario and his team, Antonio, they did typically 10 iterations. We find like 2 or 3 iterations is all you need to reach convergence. And then you end up with 10,000 CI calculations that you then compare to the ground state energy over here. So this would be a select. So basically, we're not enumerating all the configurations. We're taking LUCJ informed configurations to then do a select CI. So let's just say this CI space has 1 trillion potential determinants. We're only taking 10,000, okay? And it turns out, and I won't go into this LUCJ ansatz, there's something here that I guess even Mario, we've had conversations, don't fully understand. But it's seemingly, and IBM has showed this, at low sample counts, like 10,000, 20,000 samples, it gives results very, very close to the true result. So it basically converges very quickly. If you use the select CI or some other algorithms, they tend to very slowly converge. You need more configurations to get the same quality result. So there's something really interesting about LUCJ. And again, we sort of discussed this, right? If you have an ansatz that can actually pull out the most relevant configurations and ignoring the deadwood, then that could be a benefit of this. So what do results look like? This is a 27-qubit simulation. The figure here on the right is the layout on the IBM quantum hardware. Again, it's an Eagle device. This is a 27-qubit simulation, again, using AUG-CCPV-QZ basis set. This is our active space, so it's 16 electrons, 12 orbitals. This is the water dimer. This represents the alpha electrons. This represents the beta electrons. The one thing that's really interesting to notice on this is this electron, there's 3 qubits between this one and this one. So these aren't particularly entangled. So we have these ancilla qubits here. So there's 3 points of strong entanglement, if you will. So there's a lot of interesting technical features here. Each quantum device, so IBM Cleveland has a little bit different error pattern than IBM Yonsei. So Yonsei is going to have its own kind of error patterns of its qubits. So each machine has its own personality, right? So again, these are all done in IBM Cleveland. So this is the layout here. Again, there's some interesting features that I won't really go into. Methane dimer, this is 36-qubit simulation. AUG-CCPV-QZ base set again. It's a 16 electron, 16 orbital problem. And again, you have the alpha and beta electrons. In this case, I believe there's 1, 2, 3, 4 ancilla bits that entangle the alpha and the beta spin. Oh, by the way, this paper just came out in arXiv maybe a week or 2 ago. So if you're interested, there's the archive. You can go ahead and download it. So what are the outcomes? So if you look at the potential curves on the top left, let's look at water dimer. SQD results and heat bath CI, one's in orange, one's in red. You can't tell them apart because the heat bath CI and SQD match perfectly. So basically the results we get from the classical hardware matches the quantum within 10 to the minus 4 kcal. The blue curve is CCSD full calculation, so not within an active space. And you can see that the overall curve matches pretty well. There's about a half a kcal difference or so between the gold standard result using OGCCPV, QZ base set, and CCSD parentheses T calculations. But again, as I'll show in the methane dimer, the issue here isn't the quantum device. The issue here is the choice of active space. In the case of the methane dimer, you can see the CCSD in blue, in orange CCSD, a little bit lower level theory. And then you can see SQD, heat bath CI, and CCSD parentheses T using the same active space, 16 electrons, 16 orbitals. And you can see they track each other perfectly. So the problem here isn't the choice, isn't the quantum device. The problem here is the active space that we've chosen. If we could choose the full active space, we would essentially get the same result as down here. By the way, in terms of quantum utility, these particular calculations on the quantum hardware take about 12 hours. Again, just rough numbers. Most of the expense is these multiple CI calculations, not the quantum hardware. If you do just the straight heat bath CI calculation, that takes about 8 hours. So we're not quantum utility on this, but we're really close. And again, the problem is our CI calculations. So to really dig into this a little bit more, we did some more calculations. So that, again, I reproduced the top left, the same figure, but we actually then did some larger calculations. These are all done classically in different orbitals. So instead of 16 electron, 16 orbitals, we did 16 electron, 24 orbitals using these different levels of theory, heat bath CI. This is with perturbation theory, CCSD. And you can see we start getting this really shallow minimum built. And again, just really shows that the problem here is active space choice. In this case, we did 2S, 2P active space. This includes 3S and 3P active space. So overall, the results here are really promising. We could actually do the calculations. We understand how they behave very, very well. But again, it's a far cry from a protein, right? So ultimately, we want to do this kind of protein system. Let's see if I can pop the movie again. And so today, I'm just going to tell you about most recent results we've done on larger systems. We are currently working on peptides and some larger systems. But again, I'm going to focus more on smaller. So we decided just to go after cyclohexane. It's a molecule I really love. It's got a rich conformational space. And so we wanted to see how well we can handle something simple like cyclohexane, a small organic molecule. These are test calculations I'm going to show you. They're using the STO3G basis set. So we're not going to use the large basis set. And we're also going to use fragment-based methods. And we, at lunch, after lunch, we discussed fragment MO methods. You could use FMO. We're going to use something called density matrix, DMET, density matrix embedding theory. I think Garnet Chan developed this. So the idea here is we take a fragment CH2, so we have 1, 2, 3, 4, 5, 6 CH2s, and then we use DMET to define the orbitals. So DMET's an orbital base, and so in red, I'm sort of indicating the potential orbitals that you would include in your calculations. We then take the core, the CH2, plus the entangled, they call it entangled, unfortunately, entangled orbitals, or the orbitals that most strongly interact with this fragment. We then do the calculation on quantum hardware. So with this, we can go, we've already done some drug-like molecules, and we're currently working on much larger kinds of systems. So there's a number of fragmentation approaches. We talked about fragment MO just a little while ago. I'm a big fan of divide and conquer. Both of these are kind of atom-based approaches. And I'm sort of density matrix embedding theory is growing on me. This is a orbital base, so it's a little less arbitrary. You have sort of a way in which to identify the orbitals that most interact with your fragment. So I think there's some real advantages here. So today I'm going to tell you about preliminary work we've done on DMET, on cyclohexane, and some other model systems. In this paper, we're working on it right now with IBM. We should publish it hopefully in the next few weeks. So how does this work? Again, it's a quantum-centric supercomputing. We take our molecule, we choose our fragments. Initially, the first thing we need to do is Hartree-Fock calculation, again, to get the orbitals for the whole system. We choose our fragment orbitals. We use the Schmidt decomposition as a single-value decomposition strategy to obtain the fragment plus its entangled orbitals. And you can think of it this way. This picture is not formally correct, but the idea is that you'll have a subset of orbitals that you're then going to put into the IBM quantum device that may not be ordered directly like this, but for each CH2, you'll have a collection of the occupied orbitals and then some unoccupied orbitals that we're then going to do the CI calculations on. We generate the FCI dump just like before. We use the LUCJ onsat on the quantum processing unit for each fragment. And so in this case, there's 6 fragments. So basically, if we have 6 quantum computers, we can do 6 of these at once. If we have 6 classical hardware, we can do 6 of the classical post-processing. So this is, again, trivially parallelizable. We then post-process as before on the classical hardware. But there's one other feature as we do this iteration to get to do the error mitigation. We need to optimize the global chemical potential, which is essentially the number of electrons in the total system. So we need to make sure that if we add fragment 1, 2, 3, 4, 5, 6 together, that we have the correct number of electrons for the whole system. So that's an extra part in the iteration that we need to do. So we've implemented this at Cleveland. Yeah, I mean, it was actually, it was fairly easy to do because there's lots of good open source software. And again, I think open source software is amazing. It really enables, so we didn't have to write this from scratch. So we just use sort of available software tools. Again, this is down, first system I'll show is just H18. We did 3 subsystems of 6 electrons each. This is a layout on IBM Cleveland. It's a 27-qubit calculation. I think these figures, unfortunately, are rotated a little bit relative to the previous ones, so I apologize for that. So we have the Hartree-Fock calculation for this. We have DMET SQD with 5K samples. So again, of 10, instead of 10, we're doing 5K samples. We have DMET full CI, and we have DMET CCSD. And you can see these results like overlay. The error is extremely small for this particular calculation. By the way, I believe this is maybe the largest sort of ring that's been done, hydrogen atom ring using quantum hardware, but I may have that incorrect. We can also compare to the full calculation, so the 3 fragments of 6 hydrogens each using different methods, and we can compare to the full CCSD parentheses CC calculation. And you can see in this case, as we stretch the distance, we get some errors at the little bit longer distance, but around the minimum, the agreement is quite remarkable using this procedure. And again, this is just looking at the full calculation. This is using larger sample sizes up to 10,000 for the SQD calculations. And DMET SQD, and again, you can see in this particular case they match quite well. So, and this is again a 41-qubit test run, and again, this is using STO3G, so this is not using AUG-CC-PV-QZ for these calculations. So let's go to comparing for the cyclohexane. This is 32-qubit runs, and what we have is here we have a series of conformers of cyclohexane. So chair, it has a chair conformation. It looks like you're sitting in a chair. You have a half chair. It's like a love seat where your feet are up and your back is sort of leaning against it. twist boat. So a boat is where you've got the molecule sort of sitting like this, and you can twist it a little bit. So you have a twist boat, and then you have a boat conformation. So this is DMET full CI versus DMET SQD using 10,000 samples, STO3G basis set. And again, the agreement between the two calculations is quite good. This is DMET SQD versus CCSD parentheses T at the same basis set. And again, the agreement is quite remarkable. Okay, so just kind of in summary, in this particular case, VQE is not up to the task for this particular problem. So VQE is not the way to go to do these kinds of chemistry problems. SQD or SQST is a powerful approach. And I think one of the most important things is that I think the VQE is thinking like you're running classical hardware, whereas SQD is really thinking of your quantum device as a Rolodex or something that contains all this kind of information and you're just extracting it. So it's a very, very different, you would never do that in a classical hardware, but on quantum hardware, basically when you load this LUCJ onslots, all possible slated determinants are there. It's just a matter of pulling them off, right, in the most effective way. So I think SQD is an extremely powerful approach. It required rethinking about how to do these problems. As we leave this NISQ era behind, what does the fault-tolerant future hold? I think with this DMET, we're going to be doing peptides and even small proteins in the next few months. So I think we're already doing big systems, but now if we can do big systems with ultra-high accuracy, with large basis sets, I think it gets pretty exciting. And in my opinion, quantum computing has untapped potential that could really, in terms of the slides I showed you of the different machines, this could be the next big step forward in terms of what we can do in computer hardware. I think just imagine, let's be really optimistic. Say quantum hardware could do these calculations 1,000 times faster. What would you do with 1,000 times more capability to do these kind of calculations? What kind of problems could you address? I mean, that's what you should be thinking about. Let's be pessimistic. It's only 10 times or 100 times. Still, what would you do with 100 times more performance? That means like the CI calculations I was talking about, which maybe take 12 hours, they would take a few minutes. What could you do, right? So synthetic data sets from machine learning AI, for example. There's lots and lots of things you could do with this. So I really think my gut tells me that just like a grad student that got on a Cray computer and it was 500 times faster, just as a full professor getting my code going on a GPU and it was hundreds times faster, I believe quantum computing is going to have that same impact down the line, in my opinion. Okay, I may be over optimistic, and it's sad to hear a company went out of business, but the beauty is I'm in an academic environment and I can experiment and I can try, and it's not my company that's on the line. So I think it's really exciting. This is a picture of Michele Parnell. Some of you may know he's right here, but Paolo Carloni is a dear friend of mine. When I was a 25-year-old, I spent a summer in Florence and I taught Paolo how to do MD simulations. He's now a leading researcher in Germany at Jülich, and I understand he's moving to Pisa now. But he wanted to take us out to the countryside in Tuscany and show us where he grew up. So we were staying at a quaint farmhouse out in the countryside. We got out of the car, and there was this rainbow. And so I was like, quick, everyone get together. Let me take a picture of you. But really, is quantum computing at the end of this rainbow? I don't know. In America, we say at the end of the rainbow is a pot of gold, but maybe we'll get a quantum hardware. So, yeah, that's right. It's a good eye. It's a double rainbow. You can't really make it, but it's a double rainbow. So and basically it's red, yellow, red, RGB, and then it's RGB in the inverse here. So it's red, green, blue, and then this would be red, green, blue. So it's a double rainbow. But it's a great picture, and I think a very optimistic one in terms of the future of quantum computing. So again, I mean, it's just been amazing to spend some time with everyone. And again, my deepest congratulations to having this machine installed here and taking a leading edge in the quantum computing world. I think it's a very important forward-thinking view of things, and I hope to see great things and maybe even collaborate with some folks here. So thank you for your attention.